Hello. In this presentation, we'll demo how HP 6125 XLG blade switch integrate with Cisco Nexus 5500 and 6000 switches for IRF and FCOE technology and deployment. So agenda will briefly go through the general solution overview about the IRF and the VPC technology and also FCOE deployment with Cisco Nexus switches. And then we'll quickly go through 6125 XLG hardware overview section. After that, we'll get into the lab setup to live show how 6125 IRF configuration looked like along with Nexus 6000 VPC configuration. For fiber channel over Ethernet configuration, 6125 LG will have the dedicated FCOE connection up to the Nexus 5500. And in the last section, we'll briefly go through how you can use a different method to show commands, log, and debug commands to monitor and troubleshooting 6125 XLG. Well, this presentation primarily focused on IRF and FCA deployment. 6125 XLG switch really can support many other features like layer 3 routing, trail, OpenFlow, private VLAN, queue-in-queue, and other features. For more detailed information about 6125 XLG, IRF, and FCOE deployment, the users can check another Word document for the same topology setup. So in the Word document, we really go through the same guidelines, but in more detailed sessions. And later on in the Word document, we'll have a detailed configuration line by line breakup so users can understand more about this testing environment. Let's go through a solution overview quickly. So when in the data center environment, many customers using Nexus VPC technology to bundle two Nexus switches together. On 6125 XLG side, using CommWare version 7 technology, we can bundle two or more 6125 XLG switches together to form a virtual switch cluster. So this can work really nicely with the Nexus VPC technology for the uplink LACP bundling across multiple switches. And at the same time, it can work with any host OS to support LACP teaming like Windows, Linux, or latest VMware ESXi 5.5 version. So this is a general guideline for about the IRF technology. So let's go through the FCOE technology really quick before we delve into the configuration in the lab. So for FCOE configuration and the deployment, there are really several scenarios we can work together with the Nexus switches. So first, in this design option one, so assuming your upstream Nexus switches is a pair of converged switch, so 6125 XLG can typically have two options. One is for the Ethernet, we're using VPC to allow maximum Ethernet features and flexibility. For fiber channel or using FCOE, we can use a dedicated FCOE over dedicated FCOE link. Another option will be instead of dedicated VPC link to Ethernet, we'll have a unified link to carry both Ethernet traffic and FCOE traffic. But in this scenario, you should not use VPC and IRF on both sides because you really want to make sure you can isolate your SAN Fabric A and the Fabric B configuration and traffic flow. So this one, maybe you have more cable counts, but really for you can have a better SAN A, SAN B traffic isolation, and you don't sacrifice any features for Ethernet traffic. If you really want to consolidate your cable count, the option 2 might be better, but the option 2 you lose the VPC and the IRF technology benefit. So for option 3, really it's similar to option 1. So instead of converged Nexus on the top, so pretty much the customer can dedicate a pair of Nexus switches for Ethernet side and another pair of Nexus or MDS switches for fiber channel connectivity. So in that case, the same pair of 6125 XLG switch can work with your Ethernet LAN side of Nexus peer for VPC IRF port channel, while for fiber channel FCOE side, we can use dedicated FCOE link to Nexus peer or MDS peer. So this is a lab topology. Really, in the lab topology, we kind of simulate the design option 3. So we'll use a pair of Nexus 6001 switch to pair with the 6125 XLG for Ethernet connectivity. And we'll use a Nexus 5500 pair to connect with the 6125 XLG for dedicated FCOE connection. In the lab, due to limited cabling and SIP resources, we do not have the setup of 4 cables for VPC. Pretty much we'll be using 2 cables. Actually, these 2 cables is a two 40 gig links to between 6125 XLG pair and the Nexus 6001 pair. Really, we want to demo the 6125 XLG, the 40 gig uplink, and also IRF technology at the same time. For Nexus 5500 FCOE connection, we'll use 1 cable for each fabric path for SAN connection. So this cable will kind of carry fabric A, which is a vSAN 1 in the lab, and this cable will carry the fabric B for vSAN 2 in the lab. In real deployment, you can really add more cables and bundle all the cables for Ethernet port channeling. Actually, in the lab, we'll set up the port channel on both sides, but you will just bundle one physical 10 gig link inside this port channeling. And the virtual fiber channel interface on both sides will be bind interface to the port channel interface. And on the host side, we have a blade running VMware vSphere ESXi 5.5, doing the LACP teaming with the vSphere distributed switch, and also another blade just want to show the LACP teaming not only can work with hypervisor, can also work with bare metal OS. So we loaded with the Windows 2012 R2 release, and we'll set up the NIC teaming over there using the native NIC teaming utility. So here's a quick view about 6125 XLG hardware. So if users are familiar with the general HP networking COMware concept, 6125 XLG is very similar for the operation wise. The unique point is basically the port for the port numbering. So 6125 XLG have a 40 gig uplinks. So the port numbering is really from 1/1/1 to 1/1/4. And also it has 8 uplink for 10 gig. The 10 gig numbering will be from 10 gig 1/1/5 until 1/1/12. For the downlink, because this is a blade switch sitting inside the HP blade system C7000 enclosure. So on the front side, on the server bay, the users can populate up to 16 servers. So for the internal downlink, 6125 XLG has 16 ports going to server. So the port number will be from 10 gig 1 slash 0 slash 1 all the way to 10 slash 0 slash 16. So the port 1 will go to the bay 1, port 16 will go to the bay 16 for the server bay. Besides the uplink and the downlink, 6125 XLG also have internal 4 times 10 gig link for inter-switch stacking link across adjacent bays. So if you have a 6125 XLG sitting in IO bay 1 and another 6125 XLG sitting in IO bay 2, they will be connected through this 410 gig link. The interface numbering for this 410 gig link will be 1 slash 0 slash 17 all the way to 1 slash 0 slash 20. So by default, these 4 links will be shut down. So just to prevent the traffic loop. So you can enable them for the regular interswitch spanning tree traffic, or you can enable them dedicated to the IRF technology for the IRF link. So which is what we are using in this lab. And also another information for the hardware about the port mapping is the users can log into the HP Blade System onboard administrator, and from there you can select a IO base and you can select your 6125 XLG Blade switch, and there's a port mapping sub-tab over there. If you click that, you will see the internal port mapping. Just to make sure all this number is 1 to 16 is really for server downlink internal link. So you can see for this 6125 XLG in IO Bay 1, the first internal server downlink is connecting with the server bay 1, and you can also see the server bay 1, the first CNA port, or the MAC address, and FCOE iSCSI hardware address. So this is really good for the troubleshooting how to correlate the server side information with the 6125 XLG downlink information. Okay, so let's quickly go through the IRF technology. So this is really the configuration for IRF pairing going up to Nexus 6001. So the key thing is, on the after you set up the 6125 XLG into the IRF mode, uh, the difference compared with the Nexus switches is for Nexus switches you have two management console, but for 6125 XLG with IRF technology, you really have one management console to manage. You log into the Ethernet or console for this management plane, so you can set up the virtual port channel, and the term will be the IRF over here, and you can also define the configuration for the physical link. So in the lab setup, we have two 40 gig connections going from the 6125 XLG to Nexus 6001 switch. So you can see this is IRF port channel. We set up the bridge aggregation. Under the key thing is under the bridge aggregation, you need to make sure you use a link aggregation mode dynamic. This is not the default. You have to enable it to enable the LACP negotiation with Nexus 6001. Otherwise, the channel interface will not come up on both sides. And this is a physical link. So it's like the channel group physical interface for Nexus. Over here for 6125 XLG, you need to use a port link aggregation group on the physical interface to bundle them into the same logical layer 2 interface. And then in the layer 2 interface, for the logical port channel interface, you define the trunk interface, you define the allowed VLAN list. So this is the link verification for the uplink port channel to 6001. So you can see both 40 gig interface coming up. The flag is ACDFEF, so you can read the flag description here. O flag coming up, that means the port status is good. So this is really matching the configuration for 6001. So on 6001-01, we have one port channel setup, and we have a one 40 gig link under this VPC. And it's the same thing for Nexus 6K-2. We have, you can see the LLDP information on both sides, and you can see the port channel definition. So pretty much each port channel, VPC port channel under each Nexus 6K switch will have a 140 gig link inside. And you can see on both 6K, the virtual port channel come up. Okay, before we go to the host side, let's go into the lab to verify that. So over here, I have the three switches who have been discussed. So this is a 6125 XLG switch in IRF mode. If you do the display LDP neighbor, list, you can see if we do the filter like in 40 gig, you can really see we have two links. We have the first 40 gig link from module 1. We have the second 40 gig link from the module 2. That's the reason the chassis number is starting with a 2. And it goes to the neighbor switch 6K1 Ethernet 2/1 and 6K -2 Ethernet 2/1 as well. So if you're on the Nexus switch side, if you do the display show LDP neighbor, you can see for my local Ethernet 2/1, I'm connecting with the 6125 XLG for the 40 gig uplink. Same thing going to 6K-2. And if you want to do the display current configuration for bridge aggregation 1, so that's a configuration. If you want to do the physical config, so you can see the first physical 40 gig, we bundle them into bridge aggregation 1. All the other configuration has something related with FCOE. We'll cover later. So users shouldn't worry about too much for this configuration right now. For the second 40 gig configuration, okay, if you do the display link aggregation summary, you will see bridge aggregation 1 has 2 link coming up, and you can also do the bridge aggregation 1. This is exactly the same information you see in the PowerPoint. So both links coming up, and on the so you can see the port channel is 10. If you do the show run interface PO10, if you want to include the physical, so this is how it config on the show EPC. You can see the port channel is up. The same thing on the 6K2. So this is pretty much we show the how you can config the 6125 XLG IRF to work together with the Nexus Switches VPC technology. Okay, so remember for the IRF technology, not only we can work with the upstream Cisco Nexus switches, we can work at the same time on any host side LACP per channel teaming method. So for server side, we have another layer 2 IRF per channel, which is a bridge aggregation 101, and it has a two 10 gig link bundled together. So this is the 10 gig going to the server NIC 1. This is the 10 gig going to the server NIC 2 to the same server. You can see the key thing over here is, we need to enable the spanning tree edge port to make sure we are not talking spanning tree with any host server side. So let's get into lab to show you. So this is for the server bay 1. For the NIC 1, which is from the switch module 1, this is another NIC, which is from the switch module in IO bay 2. So you can see both modules, both links are bundled into the bridge aggregation 101 side. So you want to make sure you define the edge port. Ignore VLAN, we'll talk about more in the FCOE configuration side. One feature personally I really like is the you can get into the any interface or any configuration mode. You really can just, instead of typing the whole command for the configuration, you can just type in the display this. So this can work with the global or configuration section. Like if you are in any QoS configuration, you can just type in the display this. It will only show you the current policy map or class map configuration. So you can see that if you do the 101 status, you can see the two links coming up. If you do the verbose 101, you can see both links coming up. So I know for my slot 1, IOBay 1, I have a VMware ESXi 5.5 hypervisor, which has the LACP teaming enabled. So let's take a look. So I know this is my server. So if we go to the I'll do the VMware VD switch side. You can see this is the LACP teaming. And if you do see, take a look at the LLDP information, you can see this is connected with the same 6125 XLG 10 1/1, the second NIC, same switch 10201. So if you take a look at LACP information, you'll see this is the bundle interface, which has the two ports as active. And also I have a Windows host, and this Windows has the NIC teaming enabled. You can see LACP is enabled, and two of the NICs are bundled together with the Ethernet 5 and Ethernet 6. And this actually the second server. If you take a look at my second port for the downlink, they are so this is the first port going to server bay 2. This is the second port going to the same server bay 2. So they are being bundled into the same bridge aggregation. So if you do the display, you can see both links coming up. So this pretty much shows the same IRF cluster can work with Nexus technology, VPC, and also can work with the VMware and Windows host side of the LACP teaming. So now let's talk about FCOE deployment and configuration. So for 6125 XLG, after you boot it up, assuming you have it running in the IRF mode, like what we are doing in the lab. So the first step is you want to make sure your system working mode is in the advanced working mode. By default, 6125 XLG, it doesn't matter if it's a standalone or IRF, it's in the standard mode. So you want to enable the advanced mode. You can change in the global configuration, and also you can do the display command to verify which system working mode you are currently at. And after that, you have to save your current configuration and reboot the switch. The switch come back, and then it will come back into the advanced mode, assuming that's a setting you applied before reboot. And with advanced mode, 6125 XLG support 3 fiber channel over Ethernet configuration. So first, 6125 XLG do not have any native fiber channel or interface. It doesn't matter if it's uplink or downlink. So the only media 6125 XLG for the physical media support will be the FCOE. So for FCOE, 6125 XLG support three modes. The first is fiber channel forwarder, and also the second one is NPV, and the third one is transit. Transit is more like a fifth snooping bridge mode. When you want to work with your data center core fiber channel network, If your core network is running Cisco Nexus MDS fiber channel switch or Brocade fiber channel switch, you want to make sure you use NPV, so we can use the NP port to talking with the upstream switch. Uh, in general, upstream core switch will be running the FCF mode. You can use a transit, but it has a less intelligence. It's more like a basic FIP snooping bridge features. So in this demo, we'll just focus on the NPV mode. So if you look at the fiber channel configuration, it's mainly, it has two major components. The first, you need to define the separate vSAN and FCOE VLAN and the VFC interface to make sure you have the fabric A, fabric B, SAN traffic isolation. And the second part will mainly you need to define globally and on the interface about the features for the DCB technology, including the PFC, ETS, and the DCBX. So we'll cover the detailed configuration later in the lab and in this presentation. So this is a data center bridging brief introduction. Pretty much FCOE will depend on the DCB architecture to make sure it can deliver the lossless Ethernet transport medium. So inside DCB, you have this PFC standard, you have ETS standard, and also the DCBX standard. So most of the configuration for 6125 XLG in the second component will be related to each of these sections. For the design principles, if users you can remember is we kind of have typically three options. We'll focus on the option three. Pretty much we will have a dedicated Nexus switches for our LAN access. In this case, will be 6001, and also we'll have another pair of 5500 for FCOE connection, dedicated FCOE connection. So this is a FCOE global configuration. So later on we'll go into the lab to show you the real configuration, but this is pretty much the summary of the most important configuration. You can see you need to enable your advanced mode for system working mode, and you want to use NPV to work with the Nexus or MDS for the fiber channel side, and you want to define your vSAN for fabric A and fabric B. You want to define your FCOE VLAN and map them to the vSAN. And this is really for the DCBX priority group. So pretty much we define for the .1p values uh, for the A bits, how they can internally map into the local priority group. These same values will also be advertised to the peer switch or peer CNA. For the peer CNA side, will advise how the CNA side you want to configure your site to map this configuration. And this traffic classifier and the traffic behavior is more like class map and policy map for Cisco terms. Pretty much we want to use the advanced access list 4000, which is matching the Ethernet header 8906, which is the FCOE traffic, and 8914, which is the FIP traffic. We want to match them, and we want to mark their layer 2.1p value at 3, and we want to create this QoS policy. And later on, for this QoS policy, we'll apply it under the interface. And this policy definition is part of the DCBX application protocol implementation. So we'll exchange this information with the peer CNA, so the CNA will understand how they want to classify the traffic on their side as well. Remember, this is for fiber channel. You want to the top important thing is you want to make sure your fabric A and fabric B traffic being totally isolated from each other. So we have two links. Each link will carry one link will carry fabric A, another link will carry fabric B. So for the first switch module, we have this link going to the 5500-1. For second link will from the LB2 6125 XLG module going to Nexus 5500-2. Remember, in the lab, we only have one physical 10 gig. In the real-time deployment, you can uh, link up to multiple 10 gig interface, and you can bundle them into the same logical layer 2 network interface. So you can see for the physical interface, we bundle them to the first link, we bundle them to bridge aggregation group 10. The second link will use a different bridge aggregation group for traffic isolation. And you can see for the virtual fiber channel interface, it's really didn't bound into the Ethernet. We we did bound into the logical interface. It just take advantage of the aggregate Ethernet traffic. And you want to make sure you have the right vSAN and VLAN mappings over here. And for the uplink of virtual fiber channel, you want to make sure you change the uh, fiber channel mode to the NP port. By default, it will be the F port. So you want to make sure for the uplink to the Nexus or Brocade, you want to make sure you change it to the NP port. And for the DCBX configuration and the PFC ETS configuration, this part will be the PFC configuration. So we tell the peers we want .1p3 as a no drop queue, and also for the to advertise all these DCBX exchange parameters, you really want to make sure you enable the LLDP DCBX extension. So this command, along with the previous LLDP global enable, will make sure your interface is enabled for LLDP and your interface LLDP has the DCBX TLV being exchanged with a peer. And for the DCB ETS configuration, we really will want to make sure we define the right traffic queuing for the non-FCOE traffic and the FCOE traffic. So in this case, remember in the previous one, we already defined for FCOE traffic, it's a local Q1, and for non-FCOE traffic, it will be local Q0. And pretty much the local Q0 will be mapping to the best effort. Local Q1 will be matched to the QF1. For the internal queuing, we're using the strict priority queuing plus weighted rounded queuing. And for in this case, for non-FCOE and FCOE traffic, we'll assign them to both queues into the same weighted group, weighted round robin group for the group one. And inside this group, we use a byte count to give them the right scheduling weight. So 15, 15, pretty much each queue will get 15 divided by 30, which is a 50% of the serving priority. So pretty much this queuing defined, the ETS policy defined for my non-FCOE and FCOE traffic, they will share the link with the 50% traffic ratio for each queues. And for the previous application protocol, the QoS policy, we use outbound policy statement. Pretty much this one will tell the peer CNA you want to apply the policy and the .1p for your application FCOE traffic and also for your application for FIP traffic. So this pretty much is the format of the COMWare to how the COMWare define the application protocol parameter inside the DCBX parameter standard. For the downlink, uh, pretty much all this queuing and priority we share the same configuration. The only a couple of things you want to make sure for the downlink is you want to enable your spanning tree edge port for the downlink, and also remember in typically for server side it's a converged link. So server has a two NICs, NIC 1 going to switch 1, NIC 2 going to the switch 2. For NIC, it doesn't matter NIC 1, NIC 2, each fabric, each NIC will carry both Ethernet traffic and the fiber channel over Ethernet traffic. So you on the server side, you have a one logical interface mapping to the two links, and how you can do the FCOE traffic separation is by using this command, because by default, your bridge aggregation group configuration will want to make sure each physical interface will carry the same VLAN permit list. But for the FCOE traffic, VLAN will be the different. You want to dedicate your FCOE VLAN for vSAN1 to your first NIC, and your FCOE VLAN for your vSAN2, which is your VLAN 2000, to the second NIC. So if you define this command, then you can go into the different, 10 gig interface, physical interface. You can define different FCOE VLANs. So this is how the 5500 look like. Pretty much on the 5500, you want to make sure you enable the feature FCOE, and you want to make sure you enable the NPIV. So in this case, 6125 XLG will be the NPV mode, and your 5500 Nexus Switch or MDS will be FCF mode, because you will, over the single interface, you will have a multiple FLOGI login discover coming in. You want to make sure you have the NPIV feature enabled. And of course, you need to enable the LACP for bundling and LLDP for DCBX TLB exchange. You want to make sure you have the FCOE default policy defined. You also want to make sure you have the FCOE VLAN, vSAN defined, and you have the right mapping to on the Nexus 5K side as well. And you can see on the 5K side, there's a show FLOGI database. You can see the VFC 6125, which is the virtual fiber channel facing 6125 XLG side. We have multiple logins from the 6125 itself, and also from the host side. You can see we have a multiple login from a host side into the same virtual fiber channel. This is for the 5K1, this is for the 5K2. And this is on your host side. You can see we'll just use one ESXi host as an example. You have a multiple, you have a two FCOE connections, and pretty much your first FCOE adapter, it has a two paths, and your second adapter also have the two paths, and each path has a mapping to a remote centralized LAN. Okay, let's take a look at in the lab. So if you want to take a look at the 5K connection, So you can see for the local uplink, each 6125 XLG has one 10 gig link going to one 5K. And if you want to do the configuration for the physical link, you can see it's being bundled into the bridge 10 interface. Bridge 10 only allowed for the vSAN 1000. The same thing goes to Fabric B uplink going to 5K2. You can see it's going to 20 bridge aggregation interface, only 2000 is allowed. And if you do the only do the VFC interface for the briefing, you can see we'll have 1.2 and 1.2.2, and they are in the MP mode, and the bound interface is 10 and 20, and their status is up. And since they are the trunking, so they are actually doing the trunking MP mode. So you can see this is the MP mode, this is vSAN, this is bound to the bridge aggregation 10. Let's take a look for the VFC 22. VFC 22 only allow vSAN 2 bound into the bridge aggregation 20. And if you do the downlink side, we know the downlink side will be the match to the 101. You can see this is the ignore command. Right? So the first NIC from server 1 only allow FCOE VLAN 1000. And if you take a look at the NIC 2, which is mapping to the 201 for the server 1, is only allow FCOE VLAN 2000, and they bound into the same logical layer 2 interface 101. And you do need to have the spanning tree edge port enabled. And if you want to take a look at the MPV login information, you can see we have the 101, 201 login information coming in, and our external interface we send it up to the local VFC 12, and this is a local VFC 22. So this is pretty much for the vSAN 1, this is for the vSAN 2. And another way to look at it is you can see for the 101, it's being mapped to the 12. There's another VFC 103 coming in from the server 3. 201, 203 being mapped to the VFC 22. So let's take a look at on the 5K. So the 5K1 is the vSAN 1, and the 5K2 is vSAN 2. And the 5K1, if you take a look at port channel 10, is only 1000. This is only the 2000. And if you take a look at the show FLOGI database, you can see from the same VFC, we have the multiple login from the 6125 XLG, also 6125 XLG for the blade 1 and the blade 3 login. If you want to do the show MPV database, yeah, this is the for the vSAN 2, the login side. You can see 6125 XLG login, and for the Fabric B side, blade 1, blade 3. And so the same principle goes to, if you assuming you don't have the 5K, you don't have a 6K, and you don't have a 10 gig link, you have a 40 gig link. Uh, in the same test bed for another set of the configuration topology, we also test the 6125 XLG uplink with the 6K. So we capture some information for your reference. You can see 6K also have the 6125 going down to the 6125 XLG. So this is show interface information for the 6K, and this is a show FLOGI on the 6K. You can see the same set of the server logging, and this is for the 6K too. So of course, for this setup, we do need to change our configuration to make sure our FCOE path is going to the 6K instead of the 5K. But we just want to show, the traffic FCOE uplink can also with the 6K. So in this case, the 6K has a multi-hop also going up to another pair of Nexus switch and then going to the MDS core. So lastly, we'll cover briefly about the 6125 XLG monitoring and the troubleshooting. So you can use various display commands. You can see on the FCOE side for the 6125 XLG. We kind of already cover this command, display interface VFC 201. For the 101. Yeah, you can see the bind interface and the vSAN is up. And there are some commands you can do to show the ports command for the PFC. So display interface 10 gig, you can filter some commands. And you can do the traffic counters. You can do the queuing for the queues. And you can also do the display login buffer. And you can also do the debugging. First you need to do the terminal monitor and do the terminal debugging, and then you really want to make sure you are in the exact exit mode, instead of the configuration mode. Okay, so in order for you to do the debugging, you need to do the quit to make sure you have a various debugging command available. If you are into the config mode, if you do the debugging, you don't have anything showing up here. And you can do the turn off debug. Just make sure you'll be cautious when you do various debugging on your live network. And lastly, I really want to show you, we can turn terminal monitor, terminal debug, debug, FCOE packet interface, VFC 201. You can see the debug will be popping up. So right now we're just doing the FIP, keep alive packets. You can set up your NTP server. We'll do the undebug. Actually, the syntax will be undo, debug all. Then everything will be clear. So for the last part of this demo, I really want to do some failover testing for the FCOE traffic. So basically for my Blade 1, I'm running the hypervisor, and for the VMs, I'm running some Linux machine, and the data store will be on the remote volume through the FCOE traffic. And I have the VNC connection into this VM. So we'll download some like 3 gig ISO file and over through the Nexus 6K and come into the 6125 XLG and get into the VMs, get into the hypervisor and the VM, and then the story for the storage traffic will be coming out of the from VM and the hypervisor going into 6125 XLG and then going up to 5K. So, and while the traffic is running, we'll fill the one fabric and to see if the traffic and the download session can fill over to the other fabric. So I know for this VM, pretty much I have 2 interfaces involved. One is the display interface. This is the Blade 1. So this is the first interface. Right now, pretty much I don't have too many things going on for this blade for the NIC one. And if you want to do the 201 for the NIC 2 for the same blade, I don't have other traffic going on as well. So let's get into the 10.1.1. So I first need to get into config mode. If you do the display interface 10.1.0 again. So let's generate some traffic. Okay, I want to save. Okay, it's downloading. Okay, now we have lots of traffic going on here. Okay, we'll do the shut. Okay, now we switch to, okay, you can see now it's recovered. Two zero one. So now all the traffic is here. Maybe I'll just use this one will be better. We'll do the no shut, undo shut, do the test one more time. So the first download is already here. This is 3 gig. We'll trash it. We'll do the test again to make sure. list. Okay, we'll get this ready. Let's make sure we are up. We'll save. One, lots of traffic. We'll do shut. It's recovered. Undo shut. So this time we'll try to shut down the other link to make sure. Display 10.10.201. Okay, we should have lots of input, so this should be the FCOE traffic. We'll do the shut. Okay, so this time we see the FCOE fabric get interrupted. We'll see if it can recover. Now it recovered. For 7286, now we should see lots of input coming in, which is FCOE traffic coming in from the hypervisor. Okay, so this concludes the demo. This shows the FCOE traffic can fail over across the fabric. And thanks for watching.